writing electron configurations for ions. Before we get into writing electron configurations for ions, I want to make sure that you have a good understanding of what an ion is. Note that a neutral atom is an atom with no overall charge. That really means that it has the same number of protons, positive charges, as it has electrons, the negative charges. Now, an ion is different from a neutral atom because an ion is an atom that carries a charge, either a positive charge or a negative charge. And the reason for that is because the atom has either gained electrons or lost electrons. If an ion carries a negative charge, that means it's going to have more electrons than protons. A nickname for this type of ion is an anion. An easy way to remember this vocab word, anion, is a negative ion. Okay, an anion is a negative ion. Okay, an ion with a positive charge is an ion that has more protons than electrons. In this case, the atom lost electrons in order to form the ion. And a nickname for an ion with a positive charge is a cation. And an easy way to remember this vocab word is the fact that the T in cation looks kind of like a plus sign. Okay, so anion is a negatively charged ion. It's an atom that has gained additional electrons. And a positive ion is called a cation, and it is an atom that has lost electrons and carries a positive charge. Okay, down below is some picture diagrams of two examples. Here we're starting with neutral lithium. Lithium has 3 protons, and as a neutral atom, it has 3 electrons. It loses 1 electron to become the lithium 1+ ion. It still has the 3 protons. Atoms never gain or lose protons to become ions, but it now only has 2 electrons. Okay, it's lost 1 electron. It now has more protons than electrons, and so it carries a +1 charge. Okay, note that whenever an ion forms, the electrons are always removed from or added to the valence energy shell. Okay, when we get into looking at the orbital notation diagrams, the valence shell electrons are the electrons found in the outermost S and P sublevels. Okay, and then for the oxygen atom, as a neutral atom, oxygen has 8 protons, and it also would have 8 electrons. Those 8 positives cancel out the 8 negatives. But oxygen, in this case, has gained 2 electrons from outside itself. It now has 10 electrons, still has the 8 protons, but now it has 2 more negative charges than positive charges, and so carries a -2 charge overall. It has become the O2- ion. The name for this ion is the oxide ion. Okay, and again, note that the 2 electrons that the neutral oxygen gained, they went into the valence energy shell. So here, this second level before contained 6 electrons. And then after this oxygen atom gained 2 additional electrons, it now has 8 in this outer shell. Let's go ahead and look at some examples of how to do electron configurations for ions. So here we are asked to complete the table for the magnesium +2 ion. Okay, and we'll go through this together. Now, the first box in this table is number of electrons in the neutral atom. To find that, we need to go to the periodic table, and we will look up the magnesium ion, which is located right here. And magnesium is element number 12. Okay, that means that magnesium has 12 protons, and as a neutral atom, it also would have 12 electrons. Okay, so in the box here, for the number of electrons in the neutral atom, we would write 12. Okay, I'm actually going to go through and complete the orbital notation, the Bohr model, the Lewis diagram, all of this stuff for the neutral atom first, and then we'll make changes to it for the ion. I just want to show you how the electron configuration of an ion is related to the configuration for the neutral atom. Okay, so again, what I'm doing right now is for the neutral atom. We'll modify it to be for the ion in just a bit. So if we're talking about magnesium as a neutral atom, it has 12 electrons. I need to place 12 arrows in my orbital notation diagram, following those three rules that we talked about before. The Aufbau principle, Hund's rule, and the Pauli exclusion principle. So I'll go ahead and place my 12 electrons. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12. Okay. Now to draw the Bohr model for magnesium. Again, this is for neutral magnesium, and then we'll modify it. So it looks like there's electrons in the first energy level, the second energy level, and also in the third energy level. So that means I need to make 3 rings around the nucleus for our Bohr model, representing the 3 energy levels where electrons are found. Okay, in the first energy level, 1s, there are 2 electrons. 1, 2. In the second energy level, 2s, 2p. There's 2 from the 2s and 6 from the 2p. There's a total of 8 electrons. Okay, and then in the third energy level, 3s, there are 2 electrons. Okay, this would be the Bohr model for neutral magnesium. And if we were to write the configuration based on the Bohr model, in the first energy level, there's 2 electrons. In the second energy level, there were 8. And in the third energy level, there were 2, 2-8-2. Now, if we were to do the Lewis diagram of magnesium, again, you put the symbol of the element, Mg, and then the number of valence electrons you represent as dots. Remember, the valence electrons are the electrons on the outermost s and or p sublevels. So if we go back to the orbital notation diagram, it looks like the outermost level that's occupied is the third level. The s and p, the number of s and p electrons in the third level is a total of 2. Okay, there are 2 valence electrons, and those 2 valence electrons are represented as these 2 dots on the third shell of the Bohr model. Okay, so I would put 2 dots here. Okay, if I were to do the full electron configuration for the magnesium atom, neutral, okay, we would read off the orbital notation diagram. There's 1s, 2, 2s, 2s2, 2p6, and then 3s2. Okay, the noble gas configuration. So we go back to the periodic table, and we're going to look for the noble gas that comes just before magnesium. And it looks like that's number 10, neon. Okay, so neon would be the noble gas for this. We can go ahead and put neon in brackets. The neon in brackets is a placeholder for 1-1s2, 2s2, 2p6. And then what comes after that is the 3s2. Okay, so this is the table for the neutral atom. Let's go ahead and modify this for the ion. And hopefully this will allow you to see how the configuration of an ion is related to the configuration of the neutral atom. Okay, so number of electrons in the ion. Okay, so magnesium originally has 12 protons and 12 electrons. Okay, but magnesium has a +2 charge, which means that there are 2 more positive charges than negative charges, which means there's 2 more protons than electrons. Okay, the number of protons never changes. If we change the number of protons, we change the identity of the element. So we can't change those, but the number of electrons can change. So there's 2 more positive charges, protons and electrons. So we're stuck with the 12 protons. So we ask ourselves, 12 is 2 bigger than what number? Okay, and 12 is 2 bigger than 10. There must be 10 electrons in the ion. Okay, when the magnesium +2 ion forms, it lost 2 electrons. Okay. All right. So the question now is which 2 electrons did the magnesium atom lose when it became an ion? From the previous slide, there's that note on the bottom. It says when an ion forms, electrons are always removed from or added to the valence shell, which are the outermost S and P sublevels. So going back to the orbital notation diagram for the magnesium element, it looks like the 3s is our outermost level of, that's occupied by electrons, and the S and P levels or sublevels on the third energy level only have a total of 2 electrons in them. Okay, the 2 electrons that were lost were the 2 electrons in the 3s orbital. Okay, so that also means if I go to my Bohr model, we're losing these 2 electrons from the outermost level, and we're left with the 2 energy levels that were closest to the nucleus. Okay, that also means our configuration based on the Bohr model is not 2-8-2. We lost those outermost 2 electrons, so it's now just 2-8. The Lewis diagram, remember, is based on the number of valence electrons. There were originally 2 valence electrons, but we lost those, so those go away. Now, by convention, when we're working with a positive ion, we're drawing the Lewis structure for it. After those valence electrons get removed to form the positive ion, we put brackets around it, and then we indicate the charge. So in this case, Mg2+. That would be the Lewis diagram for the magnesium ion. Okay, the full electron configuration of the ion. Well, again, we lost the outermost electrons, the electrons in the outermost S and Ps. And there are only 2 electrons in the 3s and 3p. That's this 3s2 term here. So we erase that. And what's left is 1s2, 2s2, 2p6. And then the noble gas configuration of the ion, again, we need to get rid of the 3s2 term. Okay, and what we're left with is just Ne. 1s2, 2s2, 2p6 is the configuration for neon. Okay, hopefully that helped you see how the electron configuration of an ion is related to that of its atom. Let's look at one more example. Actually, there's 2 more examples. We'll try to go a little bit faster through these ones. Okay, so now this time we have a negative ion. We have an anion, phosphorus 3-. Okay, so again, I think what I'm going to do is complete the table first for the neutral atom, phosphorus, and then we'll make modifications to it for the ion. So first things first, finding phosphorus on the periodic table. Phosphorus is element P, and phosphorus is located right here. It's element 15. Okay, which means that phosphorus has 15 protons, and as a neutral atom, it also is going to have 15 electrons. Okay, now if I'm going to fill out the orbital diagram for neutral phosphorus, I need to place 15 electrons. Okay, and those are the 15 electrons. Next, for the Bohr model, I'm noticing that there are electrons occupying 3 energy levels. So I will draw 3 shells or 3 rings around the nucleus. Okay, on the first energy level, there are 2 electrons. On the second energy level, 2s and 2p, there are a total of 8 electrons. And on the third energy level, there are a total of 5 electrons. Okay, if we were to do the configuration based on the Bohr model, in the first energy level, there are 2 electrons. In the second energy level, there are 8 electrons. In the third energy level, there are 5 electrons. To draw the Lewis diagram for phosphorus, element P, and the outermost S and P's, so 3s and 3p are our outermost S and P's, and then there's a total of 5 valence electrons there. Okay, the full configuration for the neutral atom based on the orbital diagram would be 1s2, 2s2, 2p6, 3s2, and 3p3. Okay, and the orbital, and the noble gas configuration of the ion. For the phosphorus atom, the noble gas that comes right before phosphorus, so phosphorus is element 15. The noble gas that comes before phosphorus would be noble gas number 10, which is neon. Okay, so neon would be the noble gas that comes before phosphorus. Go ahead and put neon in brackets. And then what comes after would be 3s2, 3p3. Okay, so this would be the diagram for the neutral atom phosphorus. Let's go ahead and modify this now for the ion. Okay, so phosphorus as an ion, it has a -3 charge, which means that it has 3 more negatives than it has positives. So if it had 15 positives originally, but now it has 3 more negatives than positive, it no longer has 15 electrons, but it now has 18 electrons. 18 is 3 bigger than 15. Okay, there's 3 more negatives than positives. So the number of electrons in the ion would be 18. And when the phosphide ion formed, the phosphorus atom gained 3 electrons. Okay, let's go and modify our orbital diagram. So we gained additional 3 electrons. Okay, remember when electrons are gained or lost in the formation of an ion, they're always gained or lost to the valence shell, the outermost S's and P's. It looks like there's actually 3 positions for electrons open in the 3p sublevel, which is convenient because that's exactly the number of electrons that were gained. So let's go ahead and add those in here. 1, 2, 3. Okay. We'll go over to the Bohr model. This atom gained 3 electrons, so I need to add those. 1, 2, 3. Originally it was 2-8-5, but now that we gained 3 electrons in the outermost level, it's no longer 5, 2-8-5, it's now 2-8-8. Okay, and then the Lewis diagram, we need to add our 3 electrons that were gained when the ion forms. So now there's 8 dots around it. We need to put our brackets indicating this is an ion, and then the charge, which is 3 negative. Our full electron configuration of the ion. Okay, so we added 3 electrons to the 3p3 term. So we need to update, we need to change that 3. There's no longer 3 electrons in the 3p sublevel. There are now 6. Okay, and now for the noble gas configuration. We'll go ahead and change our 3p3 to be 6. Okay, so we have Ne in brackets, 3s2, 3p6. Now that's one possibility for writing the noble gas configuration of the ion. But the thing is if we go to the periodic table, the p-3 ion, after it's gained the 3 electrons, it now has the exact same electron configuration as argon. So you could write the noble gas configuration like we have it here, but most chemists would realize that, hey, all of this is basically identical, or is identical to the electron configuration for argon. So the preferred way to write this would be just argon in brackets. Okay, and that's the noble gas configuration of the ion. Okay, one more example. V2 plus. Okay, so we go to the periodic table. We find V, which is vanadium. And vanadium is located right here. It's element number 23. So that means vanadium has 23 protons. And as a neutral atom, it's also going to have 23 electrons. So again, I'm going to do it for the neutral atom first, and then we'll modify. Okay, so 23 arrows following our 3 rules. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, 16, 17, 18, 19, 20, 21, 22, 23. This would be the orbital diagram for neutral vanadium. Our Bohr model. Okay, I noticed that there are electrons occupying the 1, 2, 3, and 4th energy levels. So I need to draw 4 shells, because there's electrons occupying up to the 4th energy level. Okay, and in the first energy level, the 1s, there are 2 electrons there. In the second energy level, 2s and 2p, there's a total of 8. In the third energy level, this is where we got to be careful. So notice there's 3s, 3p, and 3d sublevels that have electrons in them. So we need to add all those together, and that's the number of dots we would add on the third energy level or the third ring. So 2 from the 3s, 6 from the 3p, 2 and 6 is 8, plus 3 more from the 3d makes 11. So I need to add 11 dots to this third energy level. Okay, and then on the fourth energy level, there's 4s. That's the only orbital in the fourth energy level that's occupied, and there's 2 electrons there. Okay, if we were to draw or write the configuration based on the Bohr model, we would write there's 2 electrons in the first energy level, there's 8 in the second energy level, there were 11 in the third energy level, and there are 2 on the fourth energy level. The Lewis diagram symbol for vanadium is V. Valence electrons. It's electrons on the outermost S's and P's. Okay, the outermost S's and P's that are occupied, looks like we have 4s and 4p. And of the 4s and 4p, there's only a total of 2 electrons. So that means there's going to be 2 dots placed around vanadium. Again, I'm drawing this for the neutral atom first, and then I'm going to modify for the ion. The full electron configuration for the ion. So reading off the orbital diagram, we have 1s2, 2s2, 2p6, 3s2, 3p6, 4s2, and then 3d3. And the noble gas configuration of the ion. So if we go to the periodic table, again, we're going to do this of the neutral atom first. If we go to the periodic table, vanadium is element 23. The noble gas that comes just before vanadium is number 18, argon. So we're going to go ahead and put argon in brackets. And then after argon's configuration, which goes up to the 3p6, what's left after that is 4s2, 3d3. All right, so this is the table for the neutral atom vanadium. Let's modify now for the ion. Okay, so as an ion, vanadium has a positive 2 charge, which tells us that there must be more protons than electrons, and there must be 2 more protons than electrons. Okay, there's a positive 2 charge. There's 2 more protons than electrons. There's 23 protons. That number never changes. So one way to think of this is 23 is 2 bigger than what number? Okay, there's no longer 23 electrons. It must now be 21 electrons. Okay. In the formation of this ion, vanadium essentially lost 2 electrons. Okay, so now to the orbital diagram. So if vanadium lost 2 electrons to form the vanadium ion, the question is which 2 electrons from the orbital diagram actually got lost? And remember, it's always the valence electrons, the electrons found in the outermost S and P sublevels. And in the 4s is occupied by electrons, the 4p is not. but the total number of electrons in the outermost S's and P's is 2, and both of those come from the 4s. So those are the 2 electrons that got lost. Okay, so we need to come to our Bohr model and erase those 2 electrons. Go ahead and erase that entire shell because it's no longer occupied by electrons. And then all of the inner layers are what's left. For the Lewis diagram, we'll go ahead and remove those 2 valence electrons that were drawn because those were lost. We'll put brackets around the symbol and indicate that the charge is 2 positive. Okay, I noticed that I forgot to update the shell configuration based on the Bohr model. So again, we lost 2 electrons from the outermost level. The electrons that were lost would have been those, so that now the configuration based on the Bohr model is 2-8-11. And then for the full electron configuration of the ion, so again, we lost some electrons. The electrons that we lost were the ones coming from the 4s2. So we'll go ahead and remove those. We're going to leave the 3d3 as is. That one was unaffected. Okay, and then the noble gas configuration of the ion, same thing. We're going to go ahead and remove those 2 from the 4s. Okay, and now the noble gas configuration of this ion is argon plus the 3d3 electrons. Okay, so that leads us to some key questions about the noble gas configuration and why atoms become ions. Okay, so the first question is, what do you notice about the noble gas configuration of the examples that we did? Okay, if we were to go back to magnesium, we noticed that as an ion, magnesium ion had the exact same electron configuration of neon, the noble gas. Okay, when we look at the phosphide ion, P-3, we found that that ion had the exact same configuration as argon. And when we looked at the electron configuration for vanadium ion, we note that it had an electron configuration very, very similar to that of argon, with the addition of these additional 3 electrons packed into the D sublevel on the 3rd energy level. Okay, but for practical purposes, the electron configuration of the ion is essentially argon. Okay, so the answer to this question is that hopefully you noticed that when an atom becomes an ion, it attains an electron configuration of a noble gas, or extremely similar to a noble gas. Okay, and then the second question is based on this, why do you think atoms become ions? The answer is so that the atom can have an electron configuration that's very similar or identical to that of a noble gas. The noble gas configurations are the most energetically favorable, and that is a configuration that all atoms are seeking after. And so they will end up gaining or losing the number of electrons required to have an electron configuration similar to a noble gas. All right, so now at this point, we are ready to have you stop the video, work these out, and then come back and check your answers. Now that you've had an opportunity to work these out, please pause the video again and check your answers. Make sure they match the answers I have here for the aluminum ion. And go ahead and pause the video again to check your answers for the selenide ion. selenium with a 2 negative charge. And that's all for this video. Thank you for watching. I hope this was helpful, and stay tuned for the next one.